In chemistry, when we balance equations, we focus on conservation of mass. That means the amount of each element on the reactant side has to match the amount of that same element on the product side. We can think in terms of moles, and we can also think in terms of grams, but moles are usually the cleanest way to balance. For example, if we add a coefficient of 2 to water, then oxygen becomes balanced on both sides, but hydrogen is not balanced yet, so we add a coefficient of 2 to hydrogen gas on the left side. Now both oxygen and hydrogen match on both sides, so the equation is balanced. A helpful way to picture this is an assembly line. Each time 2 hydrogen molecules react with 1 oxygen molecule, they produce 2 water molecules. So if the reaction happens 4 times, then we end up with 8 water molecules total. But now imagine we start with 1 fewer oxygen molecule than we need. We can still form water for a while, but eventually oxygen runs out first. That makes oxygen the limiting reactant. If there is still hydrogen left over after oxygen is gone, then hydrogen is the excess reactant. Now let's review types of chemical reactions. One type is a synthesis reaction, where smaller substances combine to form a larger product. Another type is decomposition, where a compound breaks down into simpler substances. Another type is combustion, where a substance reacts with oxygen and produces carbon dioxide and water. We also have single replacement reactions, where one element replaces another in a compound. And we have double replacement reactions, where ions swap partners between 2 compounds. Next, let's talk about electrolytes. When you dissolve a substance in water, it may or may not produce ions. A strong electrolyte dissolves completely and forms ions. A weak electrolyte dissolves only partially, so only some ions form. A non-electrolyte does not form ions in water. Now let's talk about ionic equations. We start with a balanced chemical reaction. Then we identify which product is the precipitate using solubility rules. In this example, the precipitate is silver chloride. Next, we split apart all the substances that are aqueous, because aqueous compounds separate into ions in solution. Then we cancel any ions that appear on both sides of the equation. Those are spectator ions, meaning they do not actually participate in the reaction. After canceling spectator ions, what is left is the net ionic equation. Now let's look at combustion in more detail. In combustion, oxygen collides with a hydrocarbon like methane, producing carbon dioxide and water. In combustion analysis, the goal is to find the empirical formula and the molecular formula of an unknown compound. Here is the setup. We start with 1 gram of the unknown sample. After combustion, it produces 2 grams of carbon dioxide and 0.818 grams of water. The problem also gives us the molar mass. Step 1 is to convert the products into moles. From carbon dioxide, we can find moles of carbon. From water, we can find moles of hydrogen. Then we convert those moles into grams of carbon and grams of hydrogen. Since the original sample was 1 gram total, we can subtract the mass of carbon and hydrogen from 1 gram to find the mass of oxygen that must have been in the compound. Then we convert that oxygen mass into moles of oxygen. Now we have moles of carbon, moles of hydrogen, and moles of oxygen. We divide all 3 by the smallest number to get a whole number ratio. In this case, the ratio becomes 2 to 4 to 1. That gives the empirical formula, carbon 2, hydrogen 4, oxygen 1. Next, we use molar mass to scale up from empirical to molecular. The empirical formula mass is 44 grams per mole. The molar mass given is 88 grams per mole. 88 is 2 times 44, so we multiply the subscripts by 2. That gives the molecular formula, carbon 4, hydrogen 8, oxygen 2.